Good morning, ladies and gentlemen. It is both an honor and a great pleasure to introduce Professor Bruce Gates, a dear friend with whom I shared an office in Professor Knotinger's laboratory during our common sabbatical in 2000. Bruce teaches in the Department of Chemical Engineering at the University of California, Davis, and formerly taught at the University of Delaware and worked at Chevron. His research group is active in catalysis with a focus on supported metal complex and metal cluster catalysts that are essentially molecular and lend themselves to design and in-depth characterization by a spectroscopy and atomic resolution microscopy. His group also works on catalysis of biomass conversion with a focus on hydroprocessing. Until recently, he edited Advances in Catalysis. He serves on the US Department of Energy Basic Energy Science Advisory Committee and the North American Catalysis Society Board of Directors. Bruce, and that's, I want to finish with that, Bruce wrote the textbook Chemistry of Catalytic Processes with Katzer and Scott McGraw-Hill in 1979, and also as single author, Catalytic Chemistry, Wiley in 1992. This remarkable book at the crossing point of chemistry with chemical engineering shows that one can walk now more safely along the pathway from the catalytic site to the process. And this is precisely the subject of his plenary lecture this morning. Let us give a big hand to Bruce. The floor is yours. Thank you very much.
Michelle, thank you for the kind words. I appreciate it. You're a diplomat to the core. Thank you, Conley, and thank you, organizing team, for inviting me. It's an honor. Let's talk about molecular catalysts on supports, a vigorously investigated topic these days, well represented at this meeting. There's a subtitle, and it's about synthesis, and there's a subtitle, and it's about design, spoken with less and less confidence as we go through. The field of supported metal complex catalysts, or single-site catalysts, or atomically dispersed catalysts, is newly invigorated. It's not new. There are important industrial examples. A few are listed here. A prominent one is polymerization of ethylene. The Phillips catalyst for that process is chromium complex on silica, the support. And the science of this topic has been well represented at ICCs. So 1980, the plenary lecturer Yermakov gave us a foundational talk about this topic, full of ideas. Many of them still seem current, but not so strongly bolstered by data, because it wasn't so easy in those days. Today, it's much easier and the field moves quite briskly. And a key technique in this field is atomic resolution electron microscopy. The image you see here shows isolated gold atoms in the absence of other gold species. And as you can see from the image, the support's a zeolite. You're looking into the pores of that zeolite. So we're interested in this class of catalysts. What are they? What do they do? And there's this viewpoint built into what I'm going to say, that these are foundational. If we can make these catalysts with a high degree of structural uniformity, then we have foundational catalytic materials, and we can build up from them to understand more and more complex catalytic materials. So almost all of the catalysts in this class, in contrast to conventional supported metal catalysts, incorporate metals in a zero-valent, not in the zero-valent state of the conventional catalyst, but rather in a cationic state. So the metals that are the catalyst part of the catalytic sites are cationic, and the implication of that is the supports to which they're bonded are ligands. It doesn't mean that the only role of a support is that of a ligand, but it means the most basic role of the support in this catalyst class is that of a ligand. So what are the other ligands? Well, we start asking the question the way one asks questions about molecular species doing catalysis in solution. So the other ligands are reactants, maybe inhibitors, maybe poisons, and so forth. So we can take a strong molecular approach to this class of catalyst. How do we know what they are? Well, the characterization methods, which have improved dramatically since the time of Yermakov's plenary talk in Tokyo, are telling us lots of detail, especially so when the structures of the samples are highly uniform. The microscopy shows up first on this list because we can observe metal atoms and see them in their environment on the support under favorable conditions. So we'll see examples of this. The various spectroscopies, a number of which can be used with catalysts in the functioning state, provide lots of information about ligands, about structure, about bonding, about reactivity. And DFT becomes especially important if the samples are precisely made and the structures to be modeled are unique structures. So the term showing up on this slide is precise synthesis. That comes from Yermakov. He emphasized that term. He almost obsessed in using that term, pointing out that to start understanding catalysts in this class, we had to make them well. And that meant synthesis, not preparation in the way we use that term mostly in catalysis, but rather synthesis. And mostly it's organometallic synthesis. So that suggests the idea of making these supported catalysts with precursors, metal-containing precursors that are molecular, and bonding them to supports that are uniform, crystalline, presenting arrays of sites that are all equivalent. So as we investigate this class of catalysts, we ask questions about what are the catalytic species that are just like the questions we ask about molecular catalysts in solution. So it's the metal oxidation state. What are the ligands bonded to it? How do they change during catalysis? How can we manipulate the catalysis by changing the ligands? How can we tune the catalytic properties? But the crucial point here, connected to the precision of the synthesis, has to do with the degree of uniformity of the supported species. We are trying to beat heterogeneity. Heterogeneity is the first statement we make about most solid catalysts. And we make approximations to deal with those catalysts. What we're attempting to do for starters here is make catalysts that are not limited by intrinsic heterogeneity and lend themselves to precise characterization and deep understanding. So how could one approach precise synthesis? Well, here's a kind of guideline, simplistic perhaps. Take a reactive metal-containing precursor. It won't be a metal salt, it'll be an organometallic compound. Let it react with sites on the surface of a support that's highly uniform, crystalline, that presents a nearly uniform array of sites for bonding. and thereby make a structure bonded to the support that's analogous to a molecule. And then work on that. Do things like remove ligands, change ligands, replace ligands, let ligands react. So here's an example of a precursor molecule. We'll talk by example about this one where the green metal atom is iridium or rhodium. The groups bonded to this are ethylene ligands, pi-bonded ethylene. Those are good ones because they're reactive. And the other group bonded to the metal is ACAC, acetyl acetonate. And so the red atoms are oxygen. That's a bidentate ligand in this precursor. And what we're going to see is this precursor can react with OH groups on a number of surfaces, like oxides, make HACAC, and then bond the metal to the surface of the support through two metal-oxygen bonds, just as you see in this precursor. So here on the left is a list of precursors of catalytically interesting metals, all of them with ACAC ligands, all of which can be used in syntheses like what I've just mentioned. For us, the prototypical support is a zeolite. Why? Well, it's crystalline, not perfectly, but often close, and it presents an array of reactive sites, proton donor sites that are strongly enough proton donating that they react with the precursors. Those sites can be tuned. We can make zeolites with high densities or low densities of those sites. And if the material is nearly perfectly crystalline, then it gives us a nearly uniform array of sites. Another important point is the atoms in this support have low atomic numbers. And for contrast with metals that have high atomic numbers, we optimize the opportunity to do atomic resolution electron microscopy. So a foundational point here is we are challenged to assess the degree of structural uniformity of the catalysts we make. How can we do that? Well, here's a list of techniques, and I'm going to illustrate them because this is so central to the storyline. So we're going to look at band widths of carbonyls as metal carbonyls as probes of support surfaces, and do catalyst poisoning and so forth. So here you see some infrared spectra. There are 2 points to make from this infrared, from the set of infrared spectra. For the zeolite supported sample, you see the cartoon of it in the upper right, the iridium gem dicarbonyl. The bands are sharp, full width at half maximum, about 5 wave numbers, and we can do even better than that sometimes. That's an indicator that the sites to which the iridium carbonyl is bound are almost all the same. In contrast, if the support's a metal oxide, here it's MgO, various MgOs, then the bands are much broader. The sites to which the metal is bonded are a smear of sites, not one site. And so we have a quick, easy, inexpensive diagnostic of degree of uniformity by using carbonyl ligands on the metal to probe the surface species. There's one other point I would like you to notice about this spectrum. We'll come back to it. It's the difference in frequencies of the carbonyl bands between the good electron donor support, MgO, and the poor electron donor support, which is the acidic zeolite. That's going to be important as we consider the supports as ligands and try to understand the catalysis. Let's do poisoning. So if we have this iridium complex bonded in HY zeolite and try to poison the cyclohexene hydrogenation with a big phosphine, triphenylphosphine, it doesn't work. There's no poisoning because the phosphine's too big to get into the zeolite pores. Use a small phosphine, trimethylphosphine. It poisons the catalyst. 1 person, 1 vote. 1 phosphine, 1 iridium site. If we look at the supported complexes in zeolites, and this is a simple zeolite in the sense the pore structure is one-dimensional in this SSC53, then what we see is that all the metal is present in single atomically dispersed species, no clusters, no particles. We can make the particles. We can treat this so the metal migrates and makes particles and blows up the zeolite, but that's another topic. And what we see is that the low loading gives us essentially a random distribution of these catalytic species. So well-dispersed catalytic sites seen with the microscope. NMR is valuable in this respect. So here we've got the zeolite-supported rhodium diethylene complex enriched in carbon-13. And running the temperature from high to low leads to a broadening of that band in the spectrum. Raising the temperature from low to high gets us at the same temperature to a fully broadened band resonance. That's indicative of dynamic uniformity around the carbon-13, and from that we infer structural uniformity of the supported species. So I've shown a number of different characterizations, anecdotal. We can't do all of these for any one sample because of the experimental challenges. All of these results pointing to uniform catalytic species on a support. So let's consider this the prototypical supported catalyst. This supports the zeolite. You see a cartoon version in the upper right and a little more precise version towards the center of the representation. This is characterized by XF spectroscopy, infrared spectroscopy, observation of the metal by STEM, and by DFT modeling. And with an error, they're agreeing. So here's a supported complex that's essentially molecular, and I would assert well characterized. So with such nearly uniform species on surfaces, one has the opportunity to do calculations representing those species as essentially molecular. So then the theorist is challenged to figure out how to represent the support, which is a macro ligand, with a simpler version, a fragment of a cluster. In Dave Dixon's work, he's done something with the very simplest of models of the support, just ALOH4, and with something much more complicated, much closer representing the zeolite as a whole. And the important point of that is it didn't matter significantly which of those models of the support he used. The bond dissociation energies that he calculated for those species were internally consistent. So with such structures, one has the basis for making predictions about bond dissociation energies and steps in catalytic cycles. So here you see for ethylene hydrogenation, the calculations showing pi-bonded ethylene, hydride, ethyl, a catalytic cycle that one would expect. It looks like the Wilkinson hydrogenation. I oversimplified a little bit. Here's the image again of the gold on zeolite Y, sodium Y in this case. And what we see looking at the image is that there are in fact two sites within the crystallographically defined structure of the zeolite where the gold resides. And so I can show them T5 sites and T6 sites, and they're clearly distinguishable in the images. As we initially make the sample, we have a distribution of the gold between those two sites. After we use it as a catalyst, low temperature catalyst, it's not very stable, for CO oxidation, the distribution of the gold between the two sites changes. So there's chemistry going on. The gold's oxidation state is changing during that as well. But the mononuclear character of the catalyst, the atomic dispersion of the metal, remains. So two sites, not one. I oversimplified slightly, but very close to the model kind of catalyst that we're striving to work for. Okay, so if we can make families of nearly uniform supported catalysts, we can start doing catalysis in a systematic way. So let's now look at a family of isostructural metal complexes as pre-catalysts on support. So we're going to hold the support constant here, and we're going to vary the metal, and we're going to vary the ligands bonded to the metal. And as a catalytic test reaction, we're going to use a simple one, on its face simple, ethylene conversion with hydrogen. It makes ethane and it makes butenes. It's a ligamerization as well as hydrogenation. And we choose the simple test reaction one because it occurs under mild conditions and the catalyst is stable. But more important than that, because the reactants form ligands that provide signatures in the spectra that help us understand what the catalyst is and what it is in the functioning state. So here's the family of pre-catalysts. The same zeolite support. Iridium and rhodium are the two metals. On the left, you see iridium or rhodium gem dicarbonyl. On the right, you see ethylene ligands instead of carbonyls. And then in the middle, you could see we systematically replaced one carbonyl with one ethylene. Nature was kind to us. There's no way one could know in advance that that could be done in a metrically simple and clean way, but it worked out that way. So you're going to hear several examples whereby nature was kind to us. So catalyst testing done in a conventional way, once through flow reactor differential conversion, all standard. But sometimes the reactor's an infrared cell, sometimes it's an XF cell. So let's look at some data. In the upper right, what you see, conversion is plotted as a function of time on stream. The conversions are very low, differential. The conversion changes with time on stream because the ligand environment of the metal changes as it is operating. So we're extrapolating to the initial condition, and it's not quite kosher to do that because, of course, we must have ligands that are reactive bonded to the metal for catalysis to occur. So there are some changes occurring rapidly, bonding hydrogen, hydride. Sometimes we see that in the infrared, often not. And ethylene, and then we'll see sometimes ethyl. Okay, so let's look at the catalytic results. The turnover frequencies, the gem dicarbonyl is catalytically dead. Of course, CO is a poison. The diethylene complex gives a relatively highly active catalyst, and the one in between gives catalytic performance in between, no surprise. And the activity and the selectivity both change depending on the ligand environment of the pre-catalyst. That's for rhodium. Let's see what we get with iridium. So it's a comparable class of catalysts, and what we're seeing is, again, CO is a poison. The most active catalyst in the family has got two ethylene ligands initially, and in between we get an in-between catalytic activity. But that one's very low. So we kick the temperature substantially and increase the activity of that intermediate catalyst a lot. And what's going on? Well, the infrared spectra of the working catalyst tell us what's going on. We're removing the kind of blocking ethylene ligand that exists at the lower temperature. We make more of that species. That's a more reactive species, and we get a higher activity when we depopulate the iridium of some of the ethylene. And we also see ethyl as an intermediate. So what's important about this is it's systematic in terms of the catalyst structure, and it's systematic in terms of the catalyst performance. We're doing what people in solution catalysis often do, going through the variables one at a time and seeing that they give systematic changes in the performance of the catalyst. So I'm going to start daring to call these variables design variables. And the two design variables we've now considered are the metal and ligands other than the support. Well, the list is longer. Let's march through the list. Let's now consider the design variable metal nuclearity. That's how many metal atoms are in the species that's the catalytic species. So we can go from mononuclear metal complex to polynuclear complex or cluster. Is that important in catalysis? Sure. Let's look at an example. So here's mononuclear gold supported on cerium oxide. And the initial activity, which you see at the lower left, is relatively low, but it's not zero. The initial cationic gold species is catalytically active for this reaction. There are lots of data now verifying that result. But after a short time of operation, the activity of that catalyst increases hugely. What's going on? Well, X-ray absorption spectroscopy of the functioning catalyst tell us what's going on. So as the initial activity increases rapidly, the XAF's gold-gold contribution increases rapidly, and by the time that gold-gold average coordination number is only about 1, which on average means dimers, the catalytic activity is way up. So we change things in a significant way as the catalyst functions, and the Zanes shows that that gold is being reduced during operation in the catalysis. So all we have to do is touch the catalyst and start making clusters, and then the catalytic properties become different. So let's try to be systematic about this. Let's start working by comparing dimer catalysts with monomer catalysts. And some of our colleagues recognized the opportunity here quite some years ago. You see that at the top of the slide. I'm going to show not their data, but some more recent data, because we can bring microscopy into the story. So we're going to start with mononuclear rhodium complexes on the zeolite, essentially the prototypical catalyst we've talked about, now with rhodium as the metal, and do characterization by microscopy and XAF spectroscopy. So what do we see initially? In the back, you might not see this so well, but I'm sure you trust me that all the rhodium is site isolated. It's mononuclear rhodium, and we've blown up one part of the image to show the rhodium and done intensity analysis to show that's an isolated rhodium center. That's what we have initially. Then we treat it in hydrogen just for a little bit, just for minutes, and we start seeing pair sites show up. So here's an intensity analysis showing rhodium pairs, rhodium dimers. What happens in the catalysis? Well, of course it changes. So let's look at the selectivity. This is ethylene conversion with hydrogen. And what's happening is that the ethane formation rate is increasing as we increase the rhodium-rhodium coordination number, as we're starting to form the smallest clusters and then bigger clusters. So the catalyst is getting more like a conventional supported rhodium catalyst metal, and it's a better hydrogenation catalyst. Neighboring rhodium centers facilitate activation of the hydrogen. And then correspondingly, the selectivity for alkenes, the dimers, is going down. So we're tuning the activity and selectivity by changing the nuclearity of the supported catalyst. So what we're talking about here is an example of having made clusters from mononuclear precursors. We're going to do another example of that in just a moment, but I want to point out there's still another approach to making such supported catalysts, and that's to start with preformed metal clusters, adsorb them, and then treat them to remove ligands. Sometimes the clusters on the support can be made with high precision, and this is another example illustrating nature's kindness. So we take the mononuclear iridium in the zeolite and treat it under conditions that cause reduction in cluster formation. We ramp the temperature with the sample in hydrogen and make measurements of the spectra during the changes as the reduction is taking place. That reduction is characterized by Zanes with isosbestic points. So this is the other characterization that gives us indications of structurally uniform species on supports. one species converted to another one cleanly, stoichiometrically. What does the XF show? Well, let's look at the gold, the iridium-iridium coordination number. So it starts up, where am I? Let's start down here. It's a mononuclear species, so the iridium-iridium coordination number is indistinguishable from 0. During this treatment, clusters grow, and they grow till that coordination number becomes nearly 3, which corresponds to a tetranuclear cluster. And as that's going on, we're breaking iridium carbon bonds, we're making ethane, and we're doing reactions that are organic in the coordination sphere of the metal. And we look at that in the infrared spectrum as these changes are taking place, and we see not only are we removing carbon-containing species from the cluster, but we're making some of those that bridge between the atoms which require neighboring metal centers. And so you see intermediates that are familiar from surface science work showing how hydrogenation occurs on metal surfaces. That whole process of cluster formation can be reversed, and it can be done in a cyclic way. So we can start with the cluster, treat it in an oxidizing agent, it's just ethylene, and that fragments the cluster, and we go back to the mononuclear complex. So nature was very kind in this case and provided a way to control the formation of clusters and complexes with high yields in the synthesis, and on more than one support. So we're coming back to this. We can make other clusters in zeolites. So let's make a bigger one, a 6-atom cluster, and I'll leave out the details of the synthesis, and you won't see the images very well, so I've put a crutch in there and shown some of the metal atoms cartoonish to emphasize where they are, but we form iridium-6 clusters in the zeolite core. So this is a ship-in-a-bottle synthesis, but it's also precise. We can make just these clusters in this support. So now we've gone over 3 of the design variables. Let's do the support as a design variable. Remember, it's a ligand. Let's consider one of the simplest imaginable supports, a molecular support. So here you see a tetrairidium, and this is the work of Katz. And what Katz has shown is that he can selectively oxidize COs at the apical position of the tetrairidium to create a catalytic site, a single atom catalytic site. And just look at the opportunities for tuning this chemistry. Change the ligands on the iridium, change the ligands on the basal plane, figure out how the basal plane iridiums, which are not catalytically active, can influence the catalysis. Go listen to Alex Katz at this meeting. Now let's talk about MgO as a support. This was one of the early images showing a site isolation of metal complexes on a support, goes back to 2009 or something. And this is powder MgO as a support. A wonderful support for doing electron microscopy because highly crystalline powders present various faces, and one can do essentially the poor person's surface science on those faces using a powder sample. Let's focus on one face. It's the 110 face of the MgO powder. And this is an osmium complex. I don't have time to tell you how that was made, but it's this mononuclear osmium complex. And the important point is that one looks at that surface, the support surface, MgO 110, provides a vision so that one's looking down on columns of magnesium and oxygen atoms. And what the images show is that the osmium's directly above magnesium. So how can one understand that? Well, using structural data, XF spectroscopy, which is not specific to this face, but gives very similar results for metal oxygen distances, whatever the face and whatever the metal oxide or zeolite. We can infer the metal oxygen distances, which make very good chemical sense, do not allow one to understand this species as present on the defect-free face of MgO 111. It only fits if the top MgO ion is missing. It's a defect site. It's a cation defect site. We hear a lot about that when we talk about this class of catalyst. Let's consider the support to be a metal. How about single crystal copper? And deposition of palladium onto that under the right conditions gives site-isolated palladium. They're mononuclear species. They're good catalysts. They do hydrogenation. And so we've got a metal as a support and a supported metal catalyst that's truly mononuclear. Let's now talk about a different class of support, MOFs. They're combinations of linkers and nodes. We're going to talk about this particular MOF, which has got pretty large pores, greater than 1 nanometer in the smallest case, and greater than 3 nanometers in some of the other pores, so well-accessible sites. And the importance of the linkers are common ones in MOF chemistry. The supports are little pieces of metal oxide, 6 zirconium atoms per node. What do we know about those nodes? Well, people have done calculations and infrared spectroscopy to form models of the structures of the nodes. And they're like metal oxides, so they have hydroxyl groups and aquo groups. And so one has sites for bonding of metal complexes, and what you see is here's a model of one node. This DFT supports this one strongly. It's quite stable. So you see an OH group, and you see an aquo group, and they're close, and so they're hydrogen bonded to each other. Here's another support model, different site, this time simply OH groups. That's less well-founded computationally. So the iridium complex and the rhodium complex precursors react with these nodes. They give structures just like what we've been talking about, and they can be modeled, and people are doing calculations with these. And so we've got models of the structures that are essentially molecular, with the support being molecular. But there's a question. Where are these protons? And it's a good question because we don't know well. As we look at the infrared spectra of the metal carbonyls, and again you see wide bands characterizing the MOF node supported complexes, indicating a heterogeneity, contrasting them sharply with the zeolite. So there's complexity in the surfaces of those, quote, molecular nodes, and there's lots yet to learn about those. So they start suggesting what goes on amorphous surfaces. There's an enormous and beautiful literature of metal complexes on silica. And I show one example from the Basset group, in which they show the power of NMR spectroscopy for elucidating structures. So you see a monopodal tungsten complex and a dipodal tungsten complex, inferred from DFT combined with NMR spectroscopy. So the complexity of the amorphous materials is greater than that of the zeolites, for example, but one can deal with that, and there are lots of opportunities to get even more precise there. Just want to mention that one can put a number of metal clusters onto supports, including amorphous supports, so all the common catalyst supports. These are examples. One can use osmium, triosmium, dodecacarbonyl as a precursor, put it on MgO, treat it under conditions that in solution give a family of osmium carbonyls, and find the same family on the support. So look at the triosmium, look at the tetraosmium, look at the pentaosmium, look at the decaosmium, which can be made in high yield, as in solution. It's thermodynamically stable. So the microscopy provides tremendous understanding of what these are. So count, look at the intensity analysis and count 10 osmium atoms. So one can make structures in a precise way. Okay, let's do a little more about catalysis. Let's try to tie some of these things together. So let's now look at these various design variables. And the conditions of some of the hydrogenations vary from one set of experiments to another. I'm leaving out that fine print. This is a comparison measurements of kinetics and measurements of spectra of the functioning catalyst, olefin hydrogenation on the iridium complex bonded on MgO versus the HY zeolite. And the key point I want to make is that the predominant species in the functioning catalyst is different, one support from another. So the support as a ligand is tuning reactivity. Let's look at a nuclearity versus support effect. So mononuclear iridium on MgO, let's change the support, otherwise having the equivalent sample. You see the activity goes up. This is a good electron donor support. That's a poor one. This is a more active catalyst. Then let's go from mononuclear to tetranuclear. Let's go around this loop the other way. Let's change from mononuclear on MgO to tetranuclear on MgO, and then fragment, and then change that to the zeolite supported. So the effects of support and nuclearity are both important, and with well-defined samples, one resolves them. Let's go back to the question of the effect of the support as an electron donor ligand. So a measure of that is the frequency of the asymmetric and symmetric CO stretches in the spectrum, and I pointed that out in an earlier slide. One has a nice correlation over orders of magnitude between the turnover frequency for ethylene conversion and that measure of electron donor tendency. So the electron donating support's not a very active catalyst, and the one that's electron withdrawing really is a much better catalyst. And the MOFs with different sites, which I didn't have time to develop very well, are distinguishable. So you get two MOFs with the same site, and they're almost identical in spectra and in catalytic activity, but you go to the other site and they're different. So this correlating parameter extends to the selectivity. All right, let's call to mind the opportunity for design and hope that I'm not exaggerating too much. Let's look at the magnesia-supported rhodium diethylene complex and consider it as a catalyst for butadiene hydrogenation. It's active, but it's unselective. Now let's carbonylate that, and of course, we've poisoned it. So the mononuclear rhodium gem dicarbonyl is catalytically inactive for this diene hydrogenation. Now, let's make dimers. And this is another one of those examples of nature treating us kindly. And we've been able to make, in very high yield, rhodium dimers, and this is a bit cartoonish. The characterization of that's not sufficient to determine the structure fully, but it's clear from the XFs that it's a dimeric species. That's catalytically active for the hydrogenation, but it's unselective. Now we selectively poison that with CO. Now we've got a less active, but highly selective catalyst. And what goes on with that catalyst is it has bridging carbonyl ligands. They show up in the infrared, and they're relatively easily removed during catalysis. So we start with a catalyst that's low in activity because the carbonyl ligands are populating the rhodium centers in the dimeric structure. But over time of operation, the CO, bridging CO, leaves, the activity goes up, and the selectivity holds. Extremely high selectivity with this catalyst until we get to the point where the conversion's so high, there's hardly any butadiene left, and then the butene starts bonding to the rhodium, and we get butane formation in unselective catalyst. So the catalyst loses activity, and so we need to put some CO in the feed stream to maintain the selectivity during the operation. So what's this tell us? I'm starting to get more daring with the use of the term design variables. The metal, iridium doesn't work, rhodium does. The support needs to be a good electron donor. The zeolite doesn't work. The metal nuclearity is important. 2 works, 1 doesn't. And the other ligands on the metal are important, selective poisons if you want to call them that. The CO is necessary for selectivity in the catalysis. Okay, there's one more entry on my list of variables that I'm calling design variables. And it has to do with combinations of functions on the catalyst support. So here's what's familiar: the zeolite-supported rhodium diethylene complex, and in the same zeolite, the supported iridium diethylene complex. And so we've, of course, done the obvious experiment of putting those two metal complexes in separate particles of catalyst and using them in the same reactor. And in that case, the result's just kind of trivial. You get the average performance from the two catalysts. But if the two metal centers are near each other, then there's a dramatic effect of the one on the performance of the other. And I don't have time to explain this well, but it's about activation of the hydrogen, which the iridium does much more rapidly than the rhodium, and then spillover of that hydrogen, which affects somehow the structure of the catalytic species that are responsible for dimerization. So we put those two metal complexes nearby each other on the support, and we dramatically decrease the selectivity for dimerization. So that's the final design variable that we're going to talk about. Let's try to put this field in a little bit of perspective. You're going to hear a lot about this field at this meeting. Let's do a few snapshots. There's this enormous amount of work from the Basset group with these various metals on silica. Lots of careful synthesis and spectroscopy and theory characterizing these, and lots of detailed understanding of reaction mechanism, illustrating the power of the approach from that research group. So listen to Basset at this meeting. There are also lots of papers emerging, and some will be presented here, showing supported noble metals as site-isolated catalysts. So gold, platinum, iridium, metals that are easily reduced, but work as isolated cationic species on a number of different supports. Metal oxides, almost all of them, but not quite all. So you see a number of names. I apologize because I didn't make this a longer list, but there's a lot of work going on to understand how to make this kind of catalyst, how to understand what it is and what the catalytic sites are, and how to elucidate how to make better catalysts in that category. And a point I want to emphasize is that some such catalysts, incorporating not just oxophilic metals like the group 7 rhenium, but more noble metals like the platinum and iridium and gold, these are stable, a number of them, at quite forcing conditions, temperatures 300 and 400 degrees C for reactions of CO, like CO oxidation and the water gas shift reaction. So this is a topic that's very timely and much in evidence at this meeting. There's a lot of work that's been done earlier trying to characterize the supported cluster catalysts using reaction kinetics, combined with the various spectroscopies. I don't want to take the time to go over this. There's a lot of information, and you can see it quickly, but you won't see all the patterns. But the point I guess I want to make is that there are not always such simple patterns in the kinetics parameters characterizing ethylene hydrogenation, propylene hydrogenation. I'm not showing it, toluene hydrogenation for this class of catalysts, various metal clusters on various supports. The long and the short of that is that once we get to clusters of this size, 4 and 6 atom clusters, there's subtle complexities showing up in the catalysis that are reflected in the kinetics. And one hypothesis is that interactions between the adsorbed species are important, and the limit to what such species one can form, determined by the size of the cluster, is important in this whole story. There's much more to learn about all of this. So I'm working towards the end, and I want to try to generalize some of these results. I want them to fit in a perspective of supported metal catalysis in a broader sense, not just the essentially molecular catalysts that we and others have strived to make, but more traditional catalysts. So what are some of the results that I think bear examination in this respect? One is, let's go back to the microscopy and examine the capabilities of the microscopy. So here's some work with a cluster, at least approximately a 70 atom cluster, a bimetallic. This work could not have been done successfully with a monometallic, in which very careful intensity analysis of the images with the cluster on this very convenient 110 face of MgO allows estimates, and it's a lot of statistical work in this characterization, estimates that provide at least good models of how many metal atoms are in each column that's being examined in the image and what they are. So look at the one with the arrow, that's this one, and the analysis of these data shows that that column is iridium, iridium, rhodium, rhodium. And the other columns have other compositions and other heights showing up with the different intensities. So remember, these structures are fluxional. They're going to be changing quickly and readily, especially under the influence of an electron beam. But the microscopy is so powerful today that one can get good models, I believe, and potentially useful models of clusters even that big using the technique. It's restricted to some supports, not general to all supports. Let's look at some other results that have some generality. Look at all the literature, essentially, of metal complexes, cationic metal complexes, metal clusters, on various supports, metal oxides, zeolites, and a whole bunch of different metal oxides, and look at the EXAFS results by which people have characterized these samples. And what consistently shows up is a metal oxygen, that is metal support oxygen distance of about 2.1 angstroms, a bonding distance. And the generality of that led to suggestion a long, long time ago that even supported clusters, larger ones, have metal atoms at the interface with the support that are cationic. And that idea is coming up again as people invoke perimeter metal atoms in supported metal clusters in catalysis of a number of reactions. So let's mention some theoretical work, some earlier work by Notkarush, in which he modeled rhodium-6 on a zeolite. And a couple of points I want to emphasize about that. When he modeled the bare cluster, rhodium-6, the agreement between the structure parameters and the EXAFS data was not satisfying. Professor Rush and I had some interesting discussions at that point in the research. Then they started doing calculations for clusters that were no longer bare and found that those clusters on realistic supports having hydroxyl groups are highly reactive. They form metal hydrides, which are much more stable than the bare clusters. And they also found charged rhodium at the interface, and then they started finding structure parameters in good agreement with the experiment, the EXAFS spectroscopy. So there are a couple of general lessons I would like to think here, not only about the charge of the metals at the metal support interface, but about the lack of bare metal species on the supports. So let's recap some of these points. The metal oxygen bonding distances for supported metals, complexes and clusters, are about 2.1 angstroms with quite some generality, which points to cationic metal at the interface, stabilizing the structures. Those structures are not very stable when they're bare. So if people are modeling supported clusters and supported complexes, please pay attention and think about the interaction and not represent the metal as zero-valent metal necessarily, and not represent the metal as bare necessarily, but account for the complexities that are consequences of the reality of typical supports with reactive groups like hydroxyl groups. The other point I want to make is that I've been emphasizing examples that I think we can understand well. And synthesis has been important in getting us those kinds of samples and trying to understand what they are and how they work. But they're unusual. The typical support is far from uniform. The heterogeneity is a reality, and we need to realize it's there and try to deal with it. And one of the points I'm trying to make is that we can deal with it step by step, recognizing increasing complexity as we go to more and more complex surfaces. And I want to emphasize this again. The typical supported metal complex catalyst is not easy to understand. The Phillips catalyst for ethylene polymerization has been investigated for decades by lots of extremely good and well-equipped scientists, and they still don't understand well quite what it is or how it works. So there are catalysts that on the face may appear to be simple, but really aren't. And the other point I want to emphasize is that lots of us have been using the term for years, well-defined supported catalyst. Please be careful. Some well-defined catalysts are better defined than other well-defined catalysts, and we're looking at a moving target and looking at a field that's developing rapidly. So here's the next to the last slide. Let's go back to the list of design variables. If we think about how to design catalysts that are essentially molecular, my assertion is that the list of variables is the same, whether the catalyst works in solution or whether it works on a support. So the ligands are important. Look at the literature of homogeneous organometallic catalysis and find enormous subtle advances in steering the catalytic properties of a given metal center by changing the ligands. Sometimes the ligand is just an electron donor or electron withdrawing group, but sometimes it plays more subtle roles. So the ligand may be reacting, calling the catalytic site just the metal, maybe simplifying the ligand can be playing a role in the catalysis. So contrast the supported catalyst with those in solution. The catalysts on supports are isolated. They don't reach each other. They don't lead to formation of metal-metal bonds so readily as in solution because they are held apart from each other. And one has opportunities, taking advantage of transport phenomena, to control the influence of one site on a support on the action of another on the support by changing, for example, the distance between them because of transport effects. Obviously, another variable is the metal. Okay, and then the metal nuclearity. And here's where there's an interesting distinction between homogeneous catalysis and surface catalysis. There's not much going on with metal clusters as catalysts in solution. They are often not stable, they're not easy to make, or not easy to make in high yields. But in contrast, we surface catalysis people usually have the metal in the form of polynuclear species, clusters. So there's big opportunity here to look at the zone, which I illustrated with the rhodium and with the gold, the zone between particles or small clusters, the ones more typically investigated in catalysis, and the mononuclear species. The very smallest clusters not so easy to make, not so easy to characterize, can offer entirely new catalytic properties. The solvent's important, but for us working with surfaces, usually not. We don't use one. But think about that. The solvent in homogeneous catalysis often plays an important role, and it complicates matters. Solvent can coordinate with the metal. So in a way, we can do the surface organometallic chemistry more cleanly and more simply than one can do it in solution because we remove the complexity of the solvent. And then the issue of the separation of the sites, it harkens back to bifunctional catalysis. One thinks of things like tandem catalysis. And there are, again, lots of opportunities for catalyst design by strategic placement of the species on the supports. I should like to finish by thanking the organizers again, thanking all of you for paying attention, thanking the people on the left who did a lot of the work that I've talked about, thanking the people on the right, colleagues who've taught us a lot, and the agencies at the top who've supported our research. Many thanks.